Alright everybody, third and final video for this week that I'm taking off. Alright, so we have kinetic energy and gravitational potential energy. We've been talking a lot about energy, which is measured in joules. You guys probably remember from chemistry class that joules measured heat energy. And that's a very specific kind of energy. It's called radiant energy. Alright, we may also think of it as the temperature of an object, alright, which is a measure of actually the kinetic energy of the molecules in an object. So here's the thing. Energy is energy. It's like this number that we calculate, alright? And we know that when we do work, it's transferred from one object to another by a force, or maybe it's changed into a different kind of energy. Well, that's what we're talking about here. We have different kinds of energy, different flavors of energy, if you will. Right? We have like chocolate energy and vanilla energy, alright? It's like chocolate ice cream and vanilla ice cream. They're both ice cream. They're just different kinds of ice cream. That's the same thing with kinetic and gravitational potential energy, alright? So let's talk about kinetic energy first. We're going to do this largely in terms of equations and calculations. So what is kinetic energy? Alright, we're going to abbreviate this as capital K, capital E, KE for kinetic energy. And this is the energy of an object that is in motion. Alright? And just like all types of energy, the units are going to be joules for this. Alright? So in the end, if we were to look at everything on the right side of the equation, we would see that it would come out to joules on the right side. So we have a mass times a velocity squared, and we have this factor of a half. If you're terribly interested, I would love to show you where this equation comes from. We could do that sometime, not today. Alright? So this is how we calculate kinetic energy. When an object is in motion, it has energy because it's moving. And if you want to think about it, for an object to get moving even to begin with, a force had to act on it, right? And if that force acted on it, that must mean that that force was doing work. And if that force was doing work, then it must have transferred energy to the object. We see the effects of that energy in the motion of that object. Rad, right? Is that not cool? So the force pushes on the object, right? Changes its velocity, gives it energy, right? And that energy, we can see the effects by seeing that it is now in motion. All right? We're going to see how this transference of energy is really important in our next section. Alright, so let's do some calculations with kinetic energy. So this is the energy of motion. When something is moving, it has kinetic energy. When something is not moving, it does not have kinetic energy because it does not have any velocity. Alright? So here we go. Example number one. Let's say we have a 12,000 kilogram truck. It speeds up from 0 meters per second to 27 meters per second. So, kinetic energy we know is 1/2 mv squared. Alright? And so we can have different energies at different times. So we can have an initial energy and we can have a final kinetic energy. Alright? And that means that we can also find a change in kinetic energy. So let's look at each of these situations in this example. Alright? So we know the mass of this truck is 12,000 kilograms. Alright? We know the initial velocity is 0 meters per second. We know the final velocity is 27 meters per second. Alright? So if I want to find the initial kinetic energy, KE initial, alright, then I'm going to take a 1/2 times the mass times the initial velocity squared. Alright, so I do 1/2 times the mass of 12,000 kilograms times my initial velocity of 0 meters per second. And I'm going to square that, but let's not be goofballs here. We don't need a calculator for this. That's a 0. So when we multiply everything, we get 0 joules worth of kinetic energy, which makes total sense. This truck is not moving at the beginning. And if it's not moving, then it has no kinetic energy. Alright? After a few seconds, though, now we have a velocity, 27 meters per second. Alright? And so our velocity has changed. That means our kinetic energy has changed. So now we have a final kinetic energy. And we take 1/2 times the mass times our final velocity squared. Alright? So we can do 1/2 times my 12,000 kilograms times my velocity of 27 meters per second. We'll square that, and we get a final kinetic energy of what? A lot. All right. 4,374,000 joules worth of energy. So where did all this energy come from, right? We started with no kinetic energy. We now have 4 million joules worth of energy. Where did all of it come from? Well, that truck, right? There's a force from that engine, and that force is doing work. And by doing work, we mean that it's adding energy or subtracting energy. Well, in this case, we're seeing an increase in our energy. And for the third part, when we're talking about a change in kinetic energy, that's what we're talking about. How much did the kinetic energy actually change by? How much more energy does it have now than it did before? And we would do this simply by taking the final kinetic energy minus the initial kinetic energy, because that's how we always do changes. All right. Well, if we do this, we have 4,374,000 joules minus our initial 0 joules, and we get a positive 4,374,000 joules. So that's how much our kinetic energy changed by. And where did all of that kinetic energy come from? It came from the force of the engine doing work on the object. All right? So there it is. That's kinetic energy. So we typically want to find things like this. We want to find the kinetic energy at a specific moment, like an initial or a final. And we also want to find changes in kinetic energy, because that's going to tell us how much work was done to get that thing to do what it's doing. All right? So here's a conceptual question dealing with our equation. All right? Kinetic energy is 1/2 mv squared, right? So the question has to be, all right, which has the greater effect, doubling the mass or doubling the velocity? All right? So let's just use a couple examples here. Let's say we have a mass of 1 kilogram and a velocity of 1 meter per second. All right? It's pretty easy. When you're doing things to just check on how it's working, you look at simple numbers. All right? So I have a mass of 1 kilogram. I have a velocity of 1 meter per second squared. Yeah, that's messy, I know. Sorry, guys. And what do we get? We get a kinetic energy of 0.5 joules. Yoy. All right. That's not very much when we think about how many millions of joules we just had in the last problem. So we get a 1/2 joule when we have 1 kilogram moving at 1 meter per second squared. Or sorry, 1 meter per second. That should just be 1 meter per second. All being squared. All right? So what happens when we double the mass? All right? Well, we have 1/2 now times 2 kilograms times 1 meter per second, and we'll square that. So what do we get? We get a kinetic energy of 1 joule. So by doubling the mass, what did we do? We doubled the kinetic energy. All right? What happens when we double the velocity? Well, here I have 1/2 times 2, sorry. We'll just go with our 1 kilogram again, right? And we'll double our velocity this time. 1 kilogram times 2 meters per second squared. So look what happens in this case, right? This thing is being squared. So we're not just doubling our kinetic energy. When we square 2, we're now going to get 4. We get 2 joules worth of energy. So we don't just double like we did up here when we doubled the mass. We actually quadruple the kinetic energy by doubling the velocity. And that's because of that squared factor. All right? So the larger effect is always going to come from the velocity because of that squared that's on that velocity. All right. So now let's talk about gravitational potential energy. All right? Gravitational potential energy is all about how much energy an object has because it's in a gravitational field. So the fact that we are on the Earth right now or near the Earth means that we're being exposed to its gravitational field. And there's energy that comes just from that. All right? Now this is still energy, so it's still measured in joules. And the equation is simple. Gravitational potential energy, GPE, is equal to the mass times the acceleration due to gravity, 9.81, with no negative, all right, no negative, times the height, all right, times the height. And the reason we don't include the negative on the 9.81 is because energy does not have direction up, down, left, and right, if you remember that from work, all right? There's no direction. And that negative on the 9.81 is all about down or, along the negative y-axis. That has no meaning here for us. Energy does not have direction, so we don't include it in this equation. All right. So what do we notice about these things? So what is gravitational energy? Well, objects that are higher up off of the Earth have a greater gravitational potential energy. So why is this? All right. So if we were to let an object fall from a greater height, all right, the gravitational force would get to act on the object for a greater distance, all right? So that force times distance, that's work, all right? And that's what we mean by potential, is that energy is the potential to do work, all right? Energy is the potential to do work. So if we let that gravitational force act for a greater distance, then that means we're going to get more work to be done on it, and that means more energy is going to get put into it by the gravitational field. All right? So greater height, the farther you are away from the surface of the planet, means you have more potential energy. All right? More potential for the gravitational force to do work on that object. All right? And that means a greater energy overall. The other thing that we can say is that more massive objects have more gravitational potential energy. And that's because here, the weight is actually larger, so the force is bigger, all right? And more force means more work, and more work means more energy, all right? So this potential energy, by just raising an object off the surface of the planet, we're giving it gravitational potential energy. And that gravitational potential energy can be changed into other kinds of energy. All right? We could drop it, and what does it do as it falls? It speeds up. So gravitational potential energy is actually being converted into kinetic energy when that happens. All right? So overall, gravitational potential energy is the fact that all objects have the potential to fall, and that means work can be done on them, and that means energy. All right? So let's look at an example. We have a 178-pound person, runs up a flight of steps at a constant velocity. They start at the bottom of the steps and end at a height of 6 meters above the ground. What's their initial gravitational potential energy? What's their final gravitational potential energy? And what's the change in potential energy? All right. So, 178 pounds. Ooh, I am mean, right? Remember, if you're going to do things, you're going to have to do it in kilograms. So we're going to need to convert this thing. Oh, that is so mean, right? So remember, 178 pounds, that can get changed into newtons, all right? So we go from pounds to newtons. So 178 pounds, right? You would look this up on your little table. Go check out all those things. And I know you're not doing it right now, are you? You're not looking. All right? Okay? This is the same thing as 791.74 newtons, all right? Which we know that's the gravitational force. Divide that by 9.81, and we get 80.71 kilograms. All right. So 80.71 kilograms worth of mass, that's what we're going to use. All right. We have two heights. We have an initial height and we have a final height. All right, so h is height from that equation before. Our starting height is at the bottom of the steps. We're going to call that 0 meters. And our ending height is 6 meters above the ground. That's going to be 6 meters. All right. The acceleration due to gravity, we're going to use a positive 9.81 meters per second squared. All right. And so we'll be able to calculate our initial GPE. So initial gravitational potential energy is mass times the acceleration due to gravity times my initial height. Alright, so we have our 80.71 kilograms times 9.81 meters per second squared times my initial height of 0 meters. Ha! Initial gravitational potential energy is 0 joules, right? So at the very bottom of the steps, you have nowhere to go. You have nowhere to fall. You have no potential. Not like seriously, like, you know, you guys all have lots of potential. I'm not saying that. I'm just saying you got no potential energy, all right? You have no potential energy. So, you have no potential energy. You have nowhere to fall when you are already at the bottom of the steps. But as you climb up, you now have a gravitational potential energy up there at the very top. This has to do with the fact that you are now 6 meters above where you could fall to, all right? So, final gravitational potential energy, we'll take our 80.71 kilograms times our 9.81 meters per second squared times our initial or final height of 6 meters above the ground, and we get a final gravitational potential energy of, you can do it, punch it in your calculator, 4,750, let me erase those scribbles, 4,750.59 joules worth of energy. So where did all that energy come from? All right? You are now 6 meters higher than where you were, which means you're farther away from the surface of the planet, which means that gravity can do more work on you if it needs to. So where did all this energy come from? Like, it can't come from nowhere. As you walked up those stairs, you burned calories, and those calories got converted into potential energy by raising your body up. All right? So you now have potential energy, gravitational potential energy that you didn't have before. All right? So what was your change in gravitational potential energy? Simple. All right? Final gravitational potential energy minus initial gravitational potential energy. All right? That's our 4,750.59 joules minus 0 joules. That's silly. We know that we have increased our energy by 4,750.59 joules. All right? So, if we increased our energy by that much, that energy had to come from somewhere. Something did work. Well, you walked up the steps. You know who did the work. You did the work. You put that energy there where it wasn't before when you walked up those steps. So there you go. That's gravitational potential energy. One last little conceptual question. All right, consider the last two examples. What needs to happen for the energy of an object to change, and what do we call this? All right, so this is in all kinetic energy, gravitational potential energy. For the energy to change, all right, that means something needs to increase the energy, put energy in, or take energy out. All right? A force needs to increase or decrease the energy. All right? That has to happen. It absolutely has to happen. If there's no force that does it, then nothing's ever going to speed up, slow down, change direction, right? This is Newton's laws that are coming into effect here. So, if a force increases or decreases the energy, what do we call this? This is called work. Forces do work. What is work? Work is increasing or decreasing the energy in an object. So in this example, when we saw that we changed our gravitational potential energy of like 5,000 joules, where did that come from? Our force did work. When we look back here at the velocity changing, right? Here we had 4 million more joules at the end than we did at the beginning. Where did that energy come from? That energy came from the force of the engine. Forces do work. Work is the transfer of energy. That's what causes changes in energy. All right, guys. You are set. You are ready. Have fun on your homework. Peace.